Okay, that's fine. Thank you very much. So yes, indeed, this is part 2 of particle astrophysics at the Large Hadron Collider and beyond. Yesterday was mostly theoretical. We looked at what the standard model of particle physics actually was. We saw that it was special relativity plus quantum mechanics plus some very scary maths, and you saw the scary maths. And the questions were all amazing yesterday and showed that you were definitely paying attention and thinking in very fine detail about what was going on, so I was very impressed. So today, as I promised, we'll look at a mostly experimental lecture. That doesn't mean I'll do it in rhythmic dance or something. It means we'll focus on the actual experiments that we use to measure particles and how they work. And immediately before coming here, I was writing the chapter of a book on exactly this. So I feel like I know it as well as I possibly can at the moment, and I'll forget it again by next week. We'll also see what's wrong with the standard model, what the current problems in particle physics are, and what we hope to do. So if you have a career in particle astrophysics, what will you actually be working on? That's the other point of today's lecture. So just a reminder, these are all the particles that we have ever observed, and we've now finished the standard model, right? That was the last piece that we were looking out for, and we found it, right? So that's a very, very significant milestone, and it's much more important than most people realize. We've passed the point where we have discovered the last thing that we know we're looking for. We know the standard model can't be the final answer. We have ideas about what can be next, but we don't know which one of them is correct. And so we're now looking for something where we don't know exactly what it looks like. And that is an enormously challenging problem. I have all sorts of ways of solving this problem, which I'm playing with at the moment, but it's a very tricky one. So when people say, well, we haven't seen supersymmetry after 10 years of searching at the LHC, that doesn't actually mean very much. I had a paper with my team last year that proved that one of the best motivated supersymmetry theories would have been completely missed by all the searches so far. So we're now in a very, very interesting and challenging world. So we saw the successes of the standard model yesterday. It describes all these particles and how they interact. What doesn't the standard model do? Well, it doesn't explain where the Higgs mechanism comes from. That came up yesterday, right? We have no idea where it actually comes from. It's just made up. We don't know why there's 4 forces in nature. You know, in Lego, you can build anything you like using 1 force. You don't need 4 of them. And indeed, at the Big Bang, we like to think there was 1 force, and it was only as the universe expanded and cooled that that 1 force started to look like different forces. And we've seen an example of that. Electromagnetism and the weak force actually unify to give a single force called the electroweak force at higher energies. So the idea of a grand unified theory, put your hand up if you've heard at least of a grand unified theory. Excellent. It would be a theory that unites all the forces, and you can write them down quite easily, but everyone that's been written down so far is completely bollocks, as we say in England, right? And the reason is that it gives you behavior that we don't see. So the simplest grand unified theory, for example, shows that protons decay almost instantaneously. So you wouldn't be here. And you're probably praying for your protons to decay at this moment, but they won't. We know that the lifetime of the proton is very long. So the answer to a grand unified theory, if there is one, has to be somewhat more complicated than we expect so far. You know, and the cleverest people have spent 50 years failing to do this, not the thickies, right? So if you want to have a go at this, there's got to be some new insight which has evaded some very, very smart people. How do we add gravity? Of course, that's the most famous challenge to the standard model, and we still really have no idea how to do that. Along with that comes the existence of extra space dimensions, right? String theory is one of the best ways that we know of trying to put gravity into quantum mechanics, but you need 11 space dimensions to do it. And you may think, well, what on earth do you mean? So I'm moving my hand in 3 large space dimensions, and they're kind of wrapping around the other space dimensions if the theory is true. It sounds bizarre, but you can write a mathematical theory of that, and you can actually test it. We've searched for extra dimensions at the Large Hadron Collider, for example, but we haven't found any evidence to date so far. This connects to questions about the graviton. If we had these extra dimensions, the mass of the graviton, instead of being very, very high and impossible to discover, might be discoverable. So I actually worked on a search at CERN that excluded low-mass gravitons that come from these sorts of theories. Now, the biggest mystery that we're going to talk about for a long time today is related to this. So I got into science by looking at the night sky, and in Cornwall, in the UK, you get very, very clear skies when it's not cloudy, which is about 2 nights a year. But there's very low light pollution. So you wouldn't stick a telescope in Cornwall. You might stick about 100 million pubs, which is what they've done. But you wouldn't stick a telescope. But nevertheless, this is the kind of thing you see when it's clear in Cornwall. And you can ask what's most interesting about this picture. And, you know, to be kind of human-centric, the house is quite interesting. We don't know anywhere else yet in the universe where there's intelligent beings that can build houses. Then you look at the dots in this picture and you think, well, maybe the dots are the most interesting thing in the picture. Some of them are stars, some of them are planets, some of them are, of course, galaxy clusters, some of them are all sorts of things. We now actually think it's the stuff that you can't see in this picture which is most interesting. So there's a weird dark matter filling lots of space, and you can't see that in this picture, but it's what most particle astrophysicists are currently working on. So the first evidence that we had something like dark matter came from this amazing character. You can see by his face. I mean, his personality matches this picture, apparently. I never met him, but he looks incredible. He was watching galaxy clusters rotate round each other in the 60s, and he found that the prediction of their speed as you go out in radius did not match the observation. So actually, if you want to model the rotation of galaxy clusters, even Newton's theory is fine, right? The general relativistic effects are very small in that system. Basically, because the mass density is not, not super, super, super high. It's not black hole high, for example. So, as you go out in distance, what you predict from Kepler's law, which is really derived from Newton's theory. Have you heard of Kepler's law? It's this thing, is it t squared is proportional to r cubed? I never remember which way around the 2 and the 3 are. You'd be ahead of me. Yeah, okay, right. So you can derive that from Newton's equation of gravity, right? If you apply that to the mass that you see in the galaxy clusters, you get this curve. What you actually measure is this curve. So as you go out in radius, the galaxy clusters are moving faster than they should be from our knowledge. And there's two ways out of this, right? One of them is to say, well, your theory's wrong. And that means even general relativity would be wrong at this point. And the other thing is to say, well, maybe there's some mass there that you can't actually see. And if you add the extra mass, you would actually predict curve B, right? So that's one point. So he suggested that. He said, and of course, I assume lots of people disagreed with him at the time, which is where this kind of face comes from. But then you start collecting other strange evidence for dark matter. So general relativity predicts that massive objects bend light. What gravity is, according to Einstein, is the curvature of space because there's a massive object in the space. Have you heard this idea before? The classic way to think about it is, imagine I had this sheet and I didn't have the table there, I just got you to hold the sheet. And I stick a football in the middle of the sheet. And for the Australians, I mean a football, a round thing, right, that you kick around the ground. Although I do now support Port Adelaide after becoming a citizen, actually. And they stuff the Crows at the weekend. So you put a football here, and I could then get a ball bearing, and I could flick it into the thing, and it will orbit, just if I get it right, it will orbit the big ball. And that's really because it's traveling in a straight line in a curved space, and that's what gravity does, it curves the space. So in other words, massive things act exactly like the lenses in these glasses. They're just using gravity to bend the light. So you can use this principle to actually measure the mass of things independently of the visible stuff, right? This is entirely a gravitational effect. So what you do is you look for these kinds of images where you have some massive foreground object which you don't have to actually see. If I had light from here that was being bent by the gravitational lensing effect, I then, of course, extrapolate backwards, just as you've seen in diagrams of optics. And what I actually see are images corresponding to lensed objects, and they have this characteristic ring shape. And you can actually sit and work out all of the details using general relativity, and any GR textbook will have this in. And what's become amazing in the last, 50 years or so is our precision of astrophysical measurement is enough to actually see these lensing effects. And that tells us that we have an amount of dark matter in the universe. So here is an interesting picture that was taken recently. This is called the bullet cluster. What you're seeing is two galaxy clusters smacking into each other perpendicular to the line of sight. And we know that because there's a kind of shock front in this X-ray radiation here. So this is a photo of the galaxy cluster collision, and they've overlaid two colors to mean two different things. So first of all, the pink is where they detected X-rays from the system. And let me explain what happens with galaxy clusters as they hit each other. There's some gas in this cluster and in this cluster. And as the gas kind of collides with the other gas, it heats up and it starts emitting X-rays. So the X-rays tell you where the visible matter in the system is. You only get the X-rays from the visible matter, right? The dark matter is basically collisionless. It's only weakly interacting. So I would expect, I have to use my kind of fanny hands for galaxy clusters. This is not to scale, obviously. As I smack these together, the collisionless dark matter actually flies through and kind of goes straight through over here. So even from that explanation, if I were to ask you, where do I expect the dark matter to be in relation to the visible matter, would it be further or would it be closer to the middle? further, because as things heat up and radiate X-rays, they lose energy, so they slow down, right? So what they did is they said, okay, let's do some gravitational lensing, and I don't care what I can see with my eyes, or even with an X-ray detector, my gravitational lensing should tell me exactly where the mass is, and most of the mass is over here, right? So this was heralded, and I think it's correct, as absolute proof that we have dark matter in galaxy clusters, right? There is no way to explain this by modifying gravitational theory, or at least it's very, very contrived if you try and do it. People pretend it's possible, but they're deluding themselves and others, I think. You often find in science, this is kind of what you hope as a scientist. You go to conferences and, recently there's an excess of gamma rays in the galactic center, and people were thinking it was either dark matter or it was millisecond pulsars. And at the same conference, someone stood up and said, I have proved this must be dark matter. And then the next speaker stood up and said, I have proved that this cannot be dark matter. Right? So there's still a huge sociological part to science, but this, I think, is absolute proof. Now, the thing is, there's even more evidence. So there's two pieces of different evidence. There's the rotation curves, and there's also the bullet cluster and gravitational lensing. The final evidence comes from something called the cosmic microwave background. Put your hands up if you've heard of it, at least. Right, who hasn't heard of the cosmic microwave background? I will explain what it is. There's no reason you should, incidentally. Something I want to get you out of the habit of quickly is thinking that you're stupid if you haven't heard of something. You just haven't heard of it. You're not even stupid if you can't do a maths exercise. Every great physicist in history couldn't do the maths exercises when they first tried them. Right? It's a myth that some people just blitz through. So we need to understand something about the history of the universe to understand what this microwave background is. Here is the history of the universe. My father-in-law is a retired historian. He's actually one of the best historians of Australian history, certainly South Australian history. And I told him I'm a historian too. I just deal with the first 10 to the minus 10 seconds. So there was a big bang. The universe kind of expanded slowly for a bit. Then it massively blew up. That's called inflation. And then initially the universe is very hot and matter is basically dissociated. And then eventually you get to the point where you can form nuclei, but you still have electrons kind of flying around in these nuclei. And then suddenly you can actually form atoms because the universe is cold enough. And there's a massive difference between a universe where you can't have atoms and a universe where you can. And it's to do with the movement of photons. Photons, remember, are the particles of electromagnetic radiation. So they scatter off anything that's charged. So while you have electrons and protons flying around, these photons can basically bounce off them and they can't travel very far. And as soon as you form atoms, there aren't free charged particles in the universe and the photons can keep moving, right? And they're still moving today. So if we look in the sky all around us, what we actually see is this background of photons coming to us from all directions at almost exactly the same temperature. And they are the relic photons from the Big Bang. And they're in the microwave region because as the universe expands, it stretches the wavelength of the photons, right? So today, they're basically microwaves, but they would have been some other part of the electromagnetic spectrum in the past, right? So I think I've explained all of this stuff. So what we've been doing in recent years is taking very, very, very precise measurements of these microwaves. So here is a satellite called the WMAP Satellite. This is already out of date. A satellite called Planck has actually done even better at measuring these microwaves. And this is a picture of the sky, and what we're seeing is the temperature of the microwaves from different parts of the sky. And I said that they were almost exactly the same temperature, but when you zoom in 10,000 times, you see very, 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 very small wobbles in the temperature of these microwaves. So are you happy that this is just a map of the sky condensed down to 2D, and you're just seeing a wobble in the temperature of the microwaves, right? Now, these are very important. We had an excellent question yesterday about lots of questions about virtual particles and what the state of the universe is. We discussed that the state of the universe, if you take all the matter out, is just fluctuating quantum fields. It's not static. It's actually these fluctuations in the quantum fields, right? So what we're actually seeing here is the imprint of the fluctuations in the quantum fields in the early universe. The reason that the photons over here are slightly hotter is because that fluctuated upwards in temperature from the quantum behavior. And if you think about it, it's essential to have something which isn't homogeneous if you want to start forming stars and galaxies. Gravity is only attractive, right? So if somewhere is slightly more dense than somewhere else, it will start pulling in matter, right? And it will eventually start forming stars and galaxies. And of course, the process snowballs because gravity is attractive. It pulls in matter, so it's even more dense, so it pulls in even more matter. and then you start getting a star or a galaxy. You know, maybe Donald Trump is going to become a star in 2 years' time or something. So basically, if we had a totally smooth universe, you wouldn't have that process. But what you can do is you can run simulations of the structure formation in the universe, and you can compare them to this amazing measurement of the wobbles in the microwaves, and then you can test exact theories of what the universe is made of and how much stuff is in the universe, right? And so we've now got to the point where this is our best theory of astrophysics. So here, the data here is exactly the same data as you see in this picture, but the reason I have a PhD and you don't at this point is because I've spent years learning how to take something simple and turn it into something that you can't understand, right? So this is called an angular power spectrum. The x-axis is the multipole moment. I would actually have to look this up exactly to see how it's defined, because I forgot this years ago. But my cosmologist friends excitedly rave about it. The reason I want to show this to you is because the red line is our best model of astrophysics, and the black points are the data, and the agreement is basically exact, right? If you were to submit a school project with that level of agreement, you'd be called a cheat, probably, right? But they now tell us we're in the era of precision cosmology, and indeed we are. Thinking about it, we're measuring these microwaves from 30,000 years after the Big Bang, and we've constructed a theory involving the wobbles of quantum fluctuations and how they form stars and galaxies that matches the data to an absurd level, right? We really, really understand how the universe works. And what we've learnt is that the visible stuff in the universe, all the matter that I showed you earlier in the standard model of particle physics, is 4% of the universe, right? And if you think about it for even a second, that's everything you've ever learnt in school, or everything you've even thought about, right, is 4% of the universe. 23% is this weird form of dark matter. And what you can do is you literally fit an equation with the amount of dark matter in, you float the amount of dark matter, and the data tells you how much you've got, and it tells us it's about 23%. And what's highly significant is the sorts of dark matter that we get from observations of the bullet cluster or observations of galaxy rotation curves. It's always about the same amount, right? So the fact that completely independent measurements give you a similar amount of dark matter is giving you extra evidence that we have dark matter. I don't think it's even in dispute now. We have dark matter, it's there. The only thing we don't know is what it is. We also discussed yesterday that if you take all the matter out of the universe, there's this weird dark energy which is blowing the expansion of the universe outwards. It's accelerating the expansion. The last Australian physicist, or kind of adopted Australian physicist, to win a Nobel Prize in fundamental physics was Brian Schmidt for exactly this, right? His team was one of the teams which was able to show this. Now, we still have no idea what either dark matter or dark energy actually are. Dark energy, I reckon, will take 60 or 70 years, but it's a made-up number. You know, we could be surprised by something. We have no idea what it is. What we do know is that the theory of particle physics, as I said yesterday, predicts an amount of dark energy which is woeful. It's 120 orders of magnitude off, so it's just useless. I mean, so that alone tells you the standard model is clearly not the final answer. Neither can the standard model explain dark matter, right? So we really think that dark matter has to be some kind of new thing that's out there. So we know some other things about dark matter. We know it's what's called cold. That means that when you start forming galaxies, it's not moving very fast, right? So neutrinos are weakly interacting and electrically neutral, so you might wonder why neutrinos can't be dark matter. We wouldn't see them, right? They're invisible. The problem is they have a very, very small mass, and when you're trying to form galaxies, their speed is very high, and they just blow apart your attempt to form galaxies, right? I mean, I have two kids. If I try and assemble anything with a 2-year-old and a 5-year-old, they just blast it apart in front of me before I can do it, right? So they're like the neutrinos in the early universe. Perhaps I should have called them electron neutrino and muon neutrino or something like this. Now, if you basically have cold dark matter, it even helps you. It makes gravitational potential wells that matter can fall into to form structure. So we know that dark matter has to be cold. It also has to be electrically neutral. You know, if something is electrically charged, again, the photon, which is light, effectively, the photon is the particle of the electromagnetic force. So if my dark matter had a charge, then it's really just interacting with photons very strongly. So I'd see it, right? It wouldn't be dark. So it's really crucial that we have electrically neutral dark matter. That doesn't mean that you could never get photons from an interaction involving dark matter. We'll see that later. But it's a subtle difference that we'll have to go through. The dark matter has to be fairly stable. I want it to be made at the Big Bang, and it's still sitting there, right? And so that means it has to be fairly stable. Its lifetime has to be fairly long. You can have dark matter which is decaying very, very slowly, but it has to be mostly stable. That's clear, I think. It also has to be weakly interacting, and that means either it interacts only via the weak force, or it interacts by a new force which is of similar strength to the weak force. If it was interacting more strongly than that, there would be observable consequences that we don't see. So this points towards dark matter being some kind of particle, and it's called cutely a weakly interacting massive particle, or a WIMP. The competing theory for many years was the macho theory, which involved massive compact halo objects, which would be things like primordial black holes and things like this. I had a student recently, one option is that dark matter is normal matter, it's just contained in black holes which were made at the Big Bang, and that's why you can't see it. And I had a student recently say, who wrote a paper showing that this would disturb the cosmic microwave background, so we would have been able to see this to some extent. So it's actually very hard to make primordial black hole dark matter work for any particular mass of the primordial black hole. So I think the WIMP hypothesis is basically correct. Also, we've never gone very far in history without discovering a whole slew of new particles. So there could be all sorts of things around the corner which are basically explaining dark matter. And dark matter is our first hint that they're basically there. So one of the ways that we can discover dark matter, as we'll see, is at the Large Hadron Collider. So this is our highest energy accelerator to date. It's located at CERN. It's on the French-Swiss border. When I lived there for a number of years, I lived in France, not Switzerland, because the rent is cheaper and the cheese and the wine are absolutely spectacular. No one's ever been invited to a Swiss cheese tasting, although they have reasonable cheeses in short doses, and their fondue is incredible. So it's a 27-kilometer diameter ring. It's 100 meters underground. That's because we have cosmic ray muons flying from space all the time, and the rock actually shields the equipment from the muons. That's very important. One of my first jobs was actually watching the detector on the surface and using the muons to check that the detector was working. So they can be useful, but they're not useful when you're trying to detect other things. We accelerate protons to nearly the speed of light. You whiz them around in one direction and the other, and then you smack them together. And yesterday we discussed what's happening. It's E equals mc squared in action. We fling the protons together, their mass gets converted to energy, and that energy then gets converted into mass. But the mass that we make has nothing to do with the mass that was there beforehand. So I can make things that were never inside the proton. I'm really just making completely new things. So again, the wrong idea is that you're colliding cars together and you get bits of car afterwards. The right idea is something like you're colliding bags of nails and the nails can turn into spanners or monkey wrenches or something else, right? It's totally quantum mechanical. We can only predict the probability of certain things happening, but we understand the physics of this really surprisingly well. And I already have 200 pages of this book on my hard drive explaining how it works. How to accelerate protons? You use superconducting magnets. These are just some fun LHC facts. They're 300 degrees below zero. That's actually colder than the space between here and the sun, for example. We collide the protons 800 million times a second. We know that the interesting things that we're looking for are extremely rare. Most of the time you collide protons together, they just kind of graze off each other and don't do anything interesting. More of the time they might make a pair of jets or they might make a W boson or something. But things like the Higgs boson are produced staggeringly rarely. We had to run for years just to collect a few hundred of them. Right? So the thing that we do to get around that is we have to collide them incredibly often to try and get rare things to happen more quickly. The energy in the whole beam is about the same as a 400-ton train moving at 150 kilometers an hour. So when we have to dump the beam, you have to dump it into these kind of big metal systems which then heat up to absurd degrees. In each particular energy, in each particular collision, there's 14 tera electron volts of energy. In fact, that's the design energy. We've only got up to 13 so far, yes.
Is that 300 degrees in Fahrenheit? Absolute zero?
It's below 0 Celsius, I think. But hang on, no, it can't be because minus 274. So this is probably from an American website, which means it would be Fahrenheit, yeah. It's basically a few degrees above absolute zero, is what I remember. Right, that makes a lot more sense. Yeah, we haven't broken the laws of thermodynamics. We've broken most other things at CERN, actually, including half of these magnets, when the collider blew up the first time we tried to run it. But we haven't broken thermodynamics. Okay, often we call particle physics high-energy physics, so let's see if it is actually high energy or not. You probably don't actually know what an electron volt is, some of you. It's a unit of energy. So the LHC beams, at least in the next run, will have 7 TeV protons. So the proton's kind of kinetic energy is 7 tera electron volts. How much is 1 tera electron volt? It's 10 to the 12 electron volts. That's what the tera means. It's an SI prefix, so that's that number of electron volts. An electron volt is 10 to the minus 19 joules. It's actually defined to be the energy you get if you have an electron at rest and a 1 volt potential, and you release the electron, and I think it travels a meter or something. I can never remember these definitions now because I'm getting too old. All I know is that you have then Q times V, and you get your 10 to the minus 19 joules, right? Actually, it must be from infinity or something, because QV is basically the energy. There are school teachers here just going like this at this precise moment, as a PhD physicist doesn't know high school physics. But that is the number of joules that corresponds to 1 electron volt. So each proton has that number of joules. So most of your calculations, you use joules for energy, I'm assuming, because that's a good sensible energy for the sorts of things that we deal with. So it's not very high energy physics. This is the point. Each proton has a tiny, tiny amount of energy in it. And one of the good things you can do in physics, if you don't trust the number, and you can do this when reading the newspaper, actually, you're given all sorts of facts in newspapers which are just wrong. And you can tell they're wrong very quickly by just playing with the numbers for a bit. So what sort of energy gives us 10 to the minus 7 joules? What's the formula for kinetic energy? Anybody?
Half mv squared.
Excellent. Yeah, half mv squared. We'll take a mosquito. This is one of these questions where I'm going to have an answer. How much do you think a mosquito weighs?
1 milligram?
I said a gram, which is probably far too much. You're probably more correct. But my argument won't work if it's a milligram. So I said it was roughly a gram. A gram mosquito would be a bit of a heavyweight, actually.
After it's taken the blood.
Yes, that's true. I reckon they can go a centimetre per second, something like this. Incidentally, this is a complete tangent. Mosquitoes find you they're very, very sensitive to trace elements of carbon dioxide. So they random walk, and then if they detect a very small amount of carbon dioxide, they can start wandering in the direction which increases the carbon dioxide concentration, and then they bite you. That's how they find you, right? Which is fascinating. So if you want a very sensitive carbon dioxide detector, it's a mosquito. So if we stick this together, we get a kinetic energy which, of course, is 10 to the minus 7 joules. That's why I said it was basically a gram. So the LHC is basically like a large mosquito collider, right? You might say, well, why didn't you just get funding for 30 years? Yeah, it took 30 years to build this thing, right? Why didn't you just train mosquitoes to fly into each other? Because a circus trainer could probably do that in a couple of weeks. The answer lies in something like this. Which of these has got more water in it? A single droplet of water or an entire cloud of water? It's not a trick question. The cloud has much more water in it. There are many, many more water molecules in a cloud. And of course, as the cloud gets more dense, it turns to rain, and a single drop of water has more molecules in a fixed volume, right, but still way less molecules than the cloud. But it's the density that's important, right? That's why clouds eventually rain, right? So what we're doing is we're taking the energy of 2 mosquitoes, but we're squeezing it into a space 1,000,000,000 times smaller than a mosquito. And it's the energy density that is the same as we had just after the Big Bang. In fact, 10 to the minus 10 seconds after the Big Bang, right? So and if you think about it, actually, there's probably no way to collide protons without having them in the tiny volume, because to make a proton hit another proton head on, you're already having to have this tiny geometric area in which to do it. And the physics of accelerators and how you actually kind of focus and defocus these beams and then get them to smack is so astounding to me. I can't even pretend to understand it. It's amazing to me that you can smack these protons together, but indeed we do. So we really are looking back to the start of the universe. We're seeing things which haven't been seen on Earth ever, and haven't been seen in the universe in that kind of concentration since 10 to the minus 10 seconds afterwards. I guess there are regions of the universe that have a very high energy density nowadays, like the center of galaxies and things like this. So here's a map of the LHC ring. This isn't literally painted onto the surface of Geneva. It's just a schematic. And what's cute here is that all the old accelerators at CERN are still in use. They're used as injector rings for the LHC. So when you build a new one, you keep the old one, and you fling the protons get a wild ride where they kind of go around here a few times and then into this one for the last stage of acceleration. And if we build the next tunnel, we'll probably use this one as well. And all the villages around here in France and Switzerland have lovely shiny new town halls, because that was how they allowed people to build a tunnel 100 meters underneath them. Right? So then there's lots of different detectors around the ring. You don't just smack the protons together once, you do it lots of times. There's 2 general purpose ones. which are just designed to discover anything new, and those are ATLAS and CMS. There's ATLAS, that's what Australians work on, and there's CMS, and they both discovered the Higgs boson, for example. We had a question yesterday about why there's more matter than antimatter in the universe, and that involves something called CP violation, and there's a detector there called LHCb whose job it is to study that phenomenon and try and work out why that antimatter asymmetry is there. And then there's another one called ALICE, which looks at heavy ions. Every Christmas, they take out the protons and they stick in heavy ions and they smack those together. And you get something called a quark-gluon plasma, and it's really kind of million Kelvin weird quantum soup fluid mechanics inside a detector. And again, no idea how this works, but it's staggeringly complicated, and I salute the people that do it. So here's the ATLAS experiment. It's the best one to work on because it's closest to the canteen, which is over there, and you can kind of serve your own beer. I don't drink nowadays, partly because of the amount of beer I drank at CERN. Then there is point one here. There's a kind of complex where you have the detector, and of course it's actually 100 meters underground. And you can look at this detector and think, what on earth do all these bits of detector do? There's a bit in the middle, the inner detector. There's these things called calorimeters and so on. Actually, the basic purpose and design of these things hasn't changed in about 50 years. We've just been building more and more complicated versions of the same thing. The inside measures the momentum of particles. So the protons come in, they make new particles. Those particles decay almost immediately, and it's their decay products that we see spraying out through the detector. Right? So the middle measures the momentum of those particles, and then the outside measures the energy. And in relativistic mechanics, once you've done relativity, you'll know that if you have the momentum and the energy, you can calculate anything you want to know. So, for example, we know the mass of the Higgs boson because we saw it decay, and we measured the momentum and energy of the decay products, and we did a quick few sums, and we found the mass of the Higgs boson. Right? So it turns out to be quite straightforward. Now, we also learn what sort of particles are. So here's the interaction point. So we're now colliding protons kind of into the plane here. And what we see, first of all, we have this tracking detector, which sees tracks and measures momentum. Then we have something called an electromagnetic calorimeter. That measures the energy of electrons and photons. And the way you measure energy is you stop particles, and as they stop, they release energy, and you pick up the energy. It's like a kind of bucket for picking up energy, and then you see what the energy was. But that also tells us if something stops here, it is an electron or a photon. And then we have a separate one for measuring jets of particles. So if you produce a quark or a gluon at the interaction point, it turns out you get a jet of particles, and you can ask me about that later if you're interested why. And so jets will stop here. So if a particle stops here, we know it ultimately came from a quark or a gluon. And then muons don't interact with any of this stuff, and we pick them up with special detectors at the outside. So what we get from ATLAS is an idea of the energy and the momentum of particles, and then we get what sort of particles we've actually seen in the detector. So the way we measure position, I mean, it used to be done that you would have a gas or something, and the particles would go through and ionize the gas, and you actually literally, with your own eyes, saw a track. And then you can measure the track with a ruler. You had to take a photo and project it on the wall to get higher precision, and you would use a ruler to measure the track. And that's fine until you're colliding protons 800 million times a second. Now, we have a lot of students and postdocs and faculty on ATLAS, but not that many. Right? So we now use what's almost like a digital camera. If I have do you know that if a charged particle is moving in a magnetic field, it moves in a curve? Have you seen that? You get circular motion. We'll see why in a minute, actually. So what I can do is stick pieces of silicon along the path of the particle. And as the particle goes through, it basically releases an electric current in the pieces of silicon. And they're special pieces of silicon called PN junctions. I had to study solid-state physics as an undergrad, and I was expecting it to be really boring, and it was incredibly interesting. I encourage you to look at solid-state physics. And it turned out to be very useful, of course. It underpins how we measure all these momenta at CERN. So you can have special doped pieces of silicon such that as a particle goes through, it releases an electric current which you can measure. So if I have a particle moving like this and I stick pieces of silicon where I know the particle's going, it's like you've all done dot-to-dot pictures as kids, I assume, where you have a load of dots and you can join them up. Right? That's exactly what we get. We get all these little currents, and then we can join them up to see where the particle went, and then we basically have a track that we can use to measure momentum. So there is the ATLAS tracker. I worked on this for a number of years. I should say that there are lots of ATLAS groups in Australia, and if you wanted to study in Australia and do LHC physics, the Adelaide group, of course, is amazing. There's an excellent group here in Sydney, I should mention, which is very, very good. There's a group in Melbourne, and there's also a new group at Monash University. So it's worth keeping in touch with me, and if you're interested in any of this work, you can get my opinion on where I think you should go to study certain things. Now, we have 135 million pixels of silicon in the middle of this thing, and then we have 6 million strips of silicon, and so pixels are clearly good for getting excellent spatial resolution. If you have lots of pixels, imagine I have these 135 million pixels, so that when all these particles are going through, I'm going to get very good measurements of exactly where the particles were. If I had less pixels, I would have much worse spatial resolution on where the particles are. Is that clear? As you go further out, you know, the density of particles passing through a unit area actually decreases as you go up away from the interaction point. So you can save a huge amount of money by starting to use strips of silicon instead of pixels. You know, it's much, much cheaper. And it turns out that the precision you'll get is roughly the same. So that's why we have silicon strips. We have another detector which doesn't involve silicon, which I won't talk about because we're getting rid of it anyway in a few years' time. Here's what the modules of silicon actually look like. So yeah, there are people whose job it is to design the electronics and design the actual detectors and glue the detectors together and bond them. I was working with a very bright lecturer in Cambridge, Sarah Williams. We're working on one of these wacky ideas I have for how to discover dark matter at the LHC. And she couldn't have a meeting one morning. She says, I have a glue test at 8 in the morning. And I wondered what on earth she meant. And what she meant was she was in the lab trying out different glues on different bits of silicon to see which one worked the best, right? So you get an amazing range of experiences in particle physics. But you can see what's happening here. We have 6 chips which you can actually bond to the silicon. And so if I get a particle passing through here, this chip can actually tell me exactly which of the 128 strips that you can't really resolve there the particle went through. So you get incredibly fine spatial resolution. And you can have 6 chips, and there's 6 chips on the other side, and then you have, I seem to remember, it's 4,800 of these modules just in the barrel region of this detector. So again, one of my first jobs was I wrote the monitoring system for this, and I had to basically write the system which showed you the output of every single one of these chips, and you would see the spikes where they weren't working, and you had to reboot the chips and all this kind of thing. It's fascinating stuff. How does this relate to momentum? Okay, what is the formula for momentum? Excellent, you can read. If I have a charged particle on the move, have you seen this before, the Lorentz force? If I have a particle moving in a magnetic field, it has a force on it, which is given by the strength of the field times the charge of the particle times the velocity. And then there's one of these utterly maddening left-hand rules, because they're meant to make life easy, but you can never remember which one you're supposed to use or what the fingers mean. If your second finger with a capital C, it's ludicrous, points along the current. Of course, if a charged particle is moving, that defines a current, so that my second finger points along that direction. If my first finger points along the field direction, then my thumb with a capital TH apparently points along the thrust. Right? I can see why this might make an idiot remember this more easily, but it's stupid to me because it's all arbitrary. So what that tells you is, look, it really is true. If I have a field which is applied perpendicular to the motion, I will get a force in another direction. As soon as I'm moving and I have a force at right angles to me, then I'm going to move like this and I end up moving in a circle. Right? It's the same as a Formula 1 car going around a hairpin or something. So then there's a centripetal force mv squared over r, and if I put them all together, and you would be able to work this out easily if you had a piece of paper in front of you, you can show that momentum is equal to the magnetic field times the charge times the radius of the curvature. So the point of measuring these tracks in our fancy silicon detectors is that we can look at how curved the tracks are. We apply a magnetic field in the ATLAS and CMS detectors to bend the particles, so we know the strength of this. We know that the charge is basically the electron charge, because it's either an electron or a muon. Okay, it could be other things, but that comes out in the wash. We then can measure the radius of curvature of the track, and if I do all that, I've measured the momentum of the particle. Right? And it turns out that for high-energy particles, we can get absurdly precise measurements of the momenta from the system, and we can do it with massive fluxes of particles through the detector. So what happens ultimately is a giant computer program studies all of the currents in this detector and can tell you in tiny fractions of a second which particles you had and what the momenta were. It's hugely impressive. Now, you can also work out how strong the magnet needs to be to actually bend these particles enough to measure their momentum. it is a 2 Tesla magnet. Now, to put that in perspective, if you go and buy a fridge magnet or you have a bar magnet in your school lab, it's usually something like microtesla, is that correct? It's something like 10 to the minus 6 Tesla, right? This is a 2 Tesla magnet. This thing is, I mean, actually it's quite light considering it's 5.7 tons. It is 5.3 meters long, and all of the detectors, these silicon detectors, are encased in this magnet. There are amusing stories about what first happened when they turned on the magnet system, because they had to clean the cavern extensively. We had all these emails about we're having a 6-week cleaning program, and I thought this was ridiculous. And then you think about it, this is the kind of field where when you turn it on, loose metal objects will just fly through the air. But in fact, here's this is one of these nice lecturing moments. Imagine that, right? And you're in the cavern and you're plugging something in over here, and then they turn the magnet on and that thing flies through your head, right? It's very serious. Screws would nut people, right, if this was allowed to happen. So they had to have a very, very careful cleanup before they turned these things on. Now, CMS has a 4 Tesla magnet because their detector's smaller and everything is hidden inside this magnet, so it has to be even stronger to make sure that you can bend particles in a smaller space. So it's crazy stuff. The only other place I've seen magnets of this kind of strength would be things like MRI scanners and that kind of thing, right? That's the other place where you need serious heavy-duty magnets. We also have other magnets around ATLAS. We have these toroid magnets. They produce a magnetic field for the muon system. And just think about what it's like to take these magnets and drop them on ropes down a tunnel, right? Because we'd already installed a lot of ATLAS when these magnets started coming down. So if you drop them, you smash the whole thing. And they did dry runs with a polystyrene-shaped magnet, and they had people, whilst it was dropped, it takes, I think, about 10 hours, and these poor saps had to abseil down the tunnel, and their one job was to just keep pushing the magnet away from their face as they were hanging in the tunnel, right? And there's people that are mad enough to do that. I hope they paid them. It's not normally the case, it's okay, so then we have the energy, that's the momentum measurer. We then have the energy measurer. Calorimeters basically work by, if I want to stop electrons and photons, I just look for a material that interacts very strongly with electrons and photons so that they'll stop. And usually you can actually have a system where you have a layer of material, then a layer that can pick up the light that's released, and then a layer of material, and so on. So that's called a sampling calorimeter. Or CMS have a bunch of clever crystals that can do everything in one go. So that's a nice thing. You can then have a separate one which is really, really good at stopping jets of particles from quarks and gluons. So that's what we do next. And then the muons are very heavy, so they're not actually stopped by the electromagnetic calorimeter, and they have their own special detector around the outside. And you can see how weird and quirky these detectors look in these pictures. So now we can measure position, momentum, energy, muons, and we know what sorts of other particles that we've seen. So we're more or less set up to start looking for something like dark matter. So we have this situation where we're colliding protons together. We can't control what's going to happen in the collisions, but we do know if there's dark matter there, some of these collisions, if it's light enough, should be producing dark matter particles, right? And unfortunately, there is a snag about dark matter, which, if you've been paying attention, should be somewhat obvious. Dark matter is dark. I once gave this talk, or something similar, at a music festival in the UK. I was on the same bill as the Pet Shop Boys and Grace Jones, and you won't know who they are because you're so young. You might know Tom York of Radiohead, because some of you are probably miserable. But it was an interesting festival with lots of different people on the bill. And of course, you're giving a lecture at 10 in the evening, and everyone was drunk. And every time I mentioned dark matter, this guy goes, "Shouldn't it be invisible matter?" And I said, "Yes, yeah, that's quite good, yeah." But then he said invisible every minute for the next 60. We had a chat afterwards. He was actually quite a fun guy. So it's invisible, right? I mean, the problem is that it's neutral and it's weakly interacting. And our detectors only measure particles that interact. It's the only thing you can do. So if you think about it, it's not charged, so it won't leave a piece of current in the silicon. It's not an electron or photon, so it won't stop in the first calorimeter. It's not related to a quark or a gluon, so it's not going to stop in the second one. And it's not a muon, so it's not going to do anything in the other detector. So if you make dark matter, it literally just escapes, right? You never see it, right? And so you're thinking, how on earth do you measure or even tell that there's an invisible particle there, right? It sounds like the Emperor's New Clothes or some physical equivalent. Now, there's one thing you can do. If I have particles coming in like this, right? This is my proton beam. What's the total momentum in this plane before they collide? Anyone?
So, repeat the question,
So if I have protons coming in like this, what's the total momentum in this plane before they collide? It's 0, because they'd have to be moving with some component in that direction. So what's the total momentum in this plane after they collide? 0, right? So if I measure stuff in this plane and the momentum balance doesn't add up to 0, then I've seen something that's leaving the detector, right? So in fact, you can make lots of neutrinos in the Standard Model, and that's how you can tell you've made neutrinos. But you can predict the sorts of signatures you see from neutrinos. If you see lots of weird things leaving the detector, you can tell that you've seen something weird. So the analogy I like to use is that, The Invisible Man was a book in, I guess, probably the 40s, something like this. And there's been various film versions over the year. I remember seeing one with Chevy Chase in the 90s. And you actually the whole point of the film is you get to know the Invisible Man, even though you never see him. And if you think about why, it's because you see his clothes, and when he, in the 90s, when he took his scarf off, his head wasn't there, So you can kind of infer lots about the Invisible Man by seeing things that are surrounding the Invisible Man. And that's exactly what happens for dark matter at the LHC. We don't just produce dark matter alone. We produce particles that either decay into dark matter, which is the jackpot, if we can see that, but we also might produce dark matter in association with other particles, and we can use their properties to tell us something about the dark matter. Without that, we would never even tell that we'd seen anything. So it's the fact that we see some things along with the dark matter that gives us hope. So here's an example of something that might happen if a theory called supersymmetry was true, which is one of the theories which can fix the problems with the Standard Model. It comes with a dark matter candidate, but it comes with lots of other particles. So our protons would collide. They might produce all sorts of particles. They decay very, very promptly to these are kind of quarks. These are electrons or muons. And then this thing is the dark matter particle. So that escapes. But it turns out that just using relativistic kinematics, you can basically take the measured energy momenta of these things and actually work out not only the mass of this thing, but also the strength of its interaction with other things. So this is a paper of mine recently, which won't make any sense to you at this point, but ask me about it later if you're interested. What we did, I kind of co-lead a team which has written a giant computer program where you can literally type in the equations of dark matter theories, and it takes all the data from astrophysics experiments and all the stuff from the Hadron Collider and lots of other things and tells you if your theory is viable. And what we did is we typed supersymmetric dark matter into this thing, and despite 10 years of searches for supersymmetric dark matter at the LHC, we were able to prove that if lots of these supersymmetric particles were light, which is exactly what you want to be able to discover, you wouldn't have seen any evidence for this so far, right? And we even uncovered a tentative evidence for a signal of supersymmetric dark matter. So if you're ever given the message as you approach particle physics, well, they haven't seen anything at the LHC, there's probably nothing there, that's it. Absolute nonsense. We've proved that the most obvious case would have evaded the current searches, and there's good reasons for this, which I could attempt to explain later if you want. So along with this, which is, I think, quite an earth-shattering result from a team of about 30 or 40 people, what I'm now developing in Adelaide is various ways to find dark matter if you don't really know what its properties are. So they range from fairly conventional, which is to take these results and work out what sorts of models we might be able to see and actually optimize searches for those models. Then they get a little bit more wacky. We can use machine learning techniques that come from credit card fraud detection. In credit card fraud detection, there's a fraud there, but you don't know what the fraud looks like. But there are machine learning techniques called unsupervised machine learning techniques where you can basically just look at some data and say, is there anything weird in this data? And it will characterize the bulk of the data, and it will characterize outliers in that data. And if you think about the LHC, that's exactly what we need to do. We need to take the energy and momentum of the particles we're seeing and our theory of the Standard Model and say, is there anything here that's a bit weird compared to what we expect? And what we're showing is it's tough, but you can make potential discoveries with dark matter using exactly the same techniques as you use in credit card fraud detection. So I'm working with a Dutch team on that at the moment. Then the wackiest idea, which I'm very excited about because it's so weird and it seems to be working. So my student Anna is working with Sarah and Holly in Cambridge on building the social network of LHC events. So it turns out that I can take, every event at the LHC after I've collided the protons is basically characterized by, I've seen some particles and they're these particles and I know their energy and momentum. Right? That's what I basically get. And then I collide the protons more and more and I collect lots of events, and each one is characterized by the particles I saw and their energy and momenta. And what you can do is say, okay, if events have kind of similar energy and momenta, then maybe they went to the same school and they're friends, right? And if events have completely different energy and momenta, well, they're not really friends, right? They don't know each other, right? And what you can do is build the equivalent of the Facebook friend network of these various events. And it turns out that when you do that, simply the number of friends an LHC event has can tell you whether it's dark matter or the standard model. And that's very, very weird and baffling, and it's because graph network analysis, which underpins the kind of structure of social media data, is actually a way of measuring topology in abstract spaces. So you can actually measure galaxy topology using the same thing. If galaxies live close to each other, they're friends, and if they live far away, they've never met, and that can actually tell you the topological structure of the universe, right? So there's an enormous amount of esoteric fun to be had in physics from wacky ideas. Okay, so the LHC at most will tell us the dark matter mass and the interactions of dark matter. Technically, though, we haven't proved that our new particle actually is dark matter. If we see a new particle at the LHC, it might have the right properties to be something like dark matter, but if you think about it, we can use this analogy. If I burn stuff on the Earth, I can see the color that it burns. You've probably seen absorption and emission spectra in chemistry. So I can burn hydrogen, and I can burn helium, and I can put the light through a prism or a Pink Floyd album cover or something. And I can see, which is wrong, by the way, the Pink Floyd album cover is completely unphysical. I think that was deliberate, probably. You get this nice spectrum, but I don't know that the sun is made of hydrogen and helium until I put the light from the sun through the same technique, right? So it's only when I compare my earthbound knowledge to my space knowledge that I can work out what's in space. And for dark matter, that corresponds to measuring the properties of the dark matter particle at the LHC, but then checking astrophysical experiments to see if we're seeing the same sort of particle in those sorts of experiments. So all the evidence I've shown you for dark matter so far is based on its gravitational interactions. We need to try and see in situ the particle interactions of dark matter. There's a couple of ways that we know how to do it. One of them is quite simple. It's called a direct search for dark matter. So the Earth is flying through space, and there's dark matter in space. So I can do the old Galilean relativity trick. If I'm the Earth walking through space, and imagine the dark matter was more or less stationary, relative to me, the dark matter is flying into me, right? And so if I stick a kind of tank of dense nuclei on the Earth, then occasionally it's very weakly interacting, but the dark matter will interact with one of the nuclei, and it will wobble the nucleus a bit, right? So I don't, that doesn't happen very often, so I stick a lot of nuclei in the detector, right? And I have to make this very clean, and I have to shield it, and all that kind of stuff. But occasionally, I will see this little wobble of a nucleus, right? So that's what we're looking for. Lots of experiments have looked for this. They haven't seen anything yet, but they're getting enormously sensitive. We're actually building one in Australia at the moment, in the stall, and we're starting a new underground lab in rural Victoria, which will have one of these experiments, which is very exciting. The other thing you can do is what's called an indirect search. So you can try and use a telescope to detect this stuff. So our theories of dark matter tell us that a dark matter particle can hit another dark matter particle, and it can annihilate to various things. And it could make protons, it could make W bosons, it could make electrons or muons. It could actually make pairs of photons. But there's no direct interaction in that case between the photon and the dark matter. It has to go through intermediate particles, and that therefore means that it happens much less often than you would like to see. But nevertheless, photons are great because they're neutral and they just fly from the source to you. So when you look at a star in the sky, you're seeing where the star is, because the light hasn't flown all around the houses to get to you, right? That's why the night sky looks as it does. So if we had photons from dark matter, we can actually detect them using special detectors, and they're very high energy if they've come from dark matter annihilation. So one way to do this is to have an array of what's called Cherenkov telescope array dishes on the surface of the Earth. So as a gamma ray from space hits the upper atmosphere, it causes an air shower. And there's something called Cherenkov radiation, which is released. If you suddenly hit a material and you're traveling faster than the speed of light in that material, you release radiation. And you may think, but you can't go faster than the speed of light, but you can't in vacuum. But different materials have different refractive indices. So again, this glass here has a different refractive index, which is what is enabling me to see you vaguely through my smudgy glasses. So you can exploit this effect, and the air itself of the Earth suddenly has a refractive index, and so this gamma ray hits it and causes this release of radiation. And all you need then are dishes that can take a photo. There's literally cameras in these dishes that take a photo of this air shower. This is called the Hess experiment. This is one example of this. It's in Namibia, in Africa. And so if I get a photo from this dish and photons from these dishes, different photos, I can actually put them together, and that tells me exactly where the photon's coming from. So this is called a stereoscopic imaging technique. And the future of this is something called the Cherenkov Telescope Array, which is really the Large Hadron Collider of gamma ray astronomy. This is something we're now involved in Australia. Lots and lots of countries are involved in this. There'll be lots of different dishes. It's being constructed at the moment, and they're all different sizes and shapes. And the idea is that you're sensitive to a huge range of energies, and you have an excellent angular resolution. So there'll be enormous astrophysical discoveries that come from this, and there will be lots of potential statements on dark matter as well, so it's particularly exciting. So I'm nominally involved in this, but have done absolutely nothing useful in 2 years, apart from attend meetings and give them money for computers. Okay, so the last thing I want to mention before wrapping up, I think is very important, and that's about careers from a physics degree. So when I grew up in the UK, no one had been to university, and I said I wanted to be a particle physicist, and people said, yeah, well, all right, okay. But you can go and do physics because it's at least a useful degree, and this was seen as a useful thing. In Australia, that message seems to be different. There's an idea that physics is a specialist thing, and you can't really do anything with a physics degree, which is nonsense. I think that one of the single most kind of useful degrees you can get is a physics degree or something closely related, because what you're really doing is you're learning to develop models of the world based on data using mathematics. So you're like an applied mathematician, but you get much more experience in computational methods and useful ways of modeling the world. There's also a big fuss about big data and machine learning techniques at the moment for good reason. I've designed a new data science course in Adelaide, which is starting again in a couple of weeks, where in the first year, you take every lecture, you have a kind of coffee table kind of survey of lots of science. It's like New Scientist every week. We pick a technique for that week, like a neural network one week or social network analysis the next week, and you study examples from physics, chemistry, geology, and biology, and health that all use the same technique to solve problems. And by the end of the course, you have this amazing ability to solve problems using all sorts of crazy techniques. So in fact, my wacky social media idea for dark matter discovery came from preparing this course. So what we're now having at Adelaide is a program where you'll do an entire program where you can do physics plus data science, or you can do biology plus data science, or chemistry, or anything you like, so that you can be maximally prepared for going off into industry or something else. So here's just a list of where people I've worked with at CERN or Cambridge or Adelaide have gone after they did their physics degree. A depressingly large number went off to earn lots of money in international banking, right? And so my brother's boyfriend, for example, did a PhD in biological fluid mechanics, knowing already he didn't want to do that for a job. He just wanted to be a banker. And he described his first week in banking as solving exactly the same equations as fluid flow in the urethra, bizarrely, but much, much quicker, and there was much more riding on the outcome, right? And he didn't come from money, and within, I think, 5 years, he bought a house in London for £750,000 in cash. Right. Exactly. That's why people don't like bankers. And what's really annoying is he's really nice. And you can't even hate him. So there we go. But there's lots of interesting challenges in banking, predicting the stock market, using clever techniques to predict the stock market. Indeed, when I was back in Cambridge a couple of weeks ago, Will Handley, who's an amazing cosmologist there, was telling me he now knows a hedge fund that will only employ physicists, for example, because they like the skill set of the physicist. My previous postdoc at Cambridge went off to do aerodynamic modeling for the Williams Formula 1 team. And I was reassured to know that she'd left, because they got much quicker when she arrived, and they got much slower last year. And indeed, she left last year. Right? So she was basically taking the same software that we use at CERN and applying it to the wind tunnel data that they had. It turns out they'd spent $7 million collecting wind tunnel data, but no one was analyzing it. Right? So when they complain about not having money in Formula 1 teams, you have to question some of the decisions. Lots of people are working in defense, and they can't say what they're doing. They have to sign these secrecy contracts. We know that there's people working in cybercrime prevention, and I think most of these are probably doing the same thing. And what's interesting, reading between the lines, most people that work for defense in South Australia are either finding ways to spy on the Chinese or finding ways for the Chinese to stop spying on us. right? And you think, couldn't you save a lot of money by just sitting in the same room for an hour and comparing notes, right? But that's, I guess, the strange world of international espionage. I mean, at least with the US, you don't need to spy anymore because Donald Trump just tweets everything that's going on. Okay, climate modeling is another application and, of course, hugely important. IT, consulting, working in the mining industry, and so on. So physics is an excellent degree to do, and I strongly encourage you to think about it if you're that way inclined. So to summarize, there's some kind of strange dark matter in the universe. We think it's some kind of particle. We hope to study its properties at the LHC. We have lots of exciting new ways for doing so, and we've so far only taken a 50th of the data that we're going to take at the LHC. So particle physics is wide open as a field at the moment, and I can point you to a book I wrote for a short booklet for the Institute of Physics in the UK a few years ago. It's pitched at third-year undergrad level, but you would get something out of it about what those challenges are. But basically, discovering the origin of the Higgs mechanism and dark matter, those are the big games in particle physics for the next 15 years or so. Lots of this involves working very closely with astrophysicists, and I think it is the most exciting, it's certainly the most exciting time of my career to be a particle physicist. You know, we can actually poke the Higgs field and study it for the first time. We have lots of data coming from other areas. You know, we're all writing papers on black holes because that links to gravitational wave astronomy. I think this is probably the most exciting period since at least the 60s and maybe even the 1920s in physics. So perhaps I'll leave it there. Thank you.